So the first thing that we're going to cover is the standard force entities included in RecurDyn Professional. And so these, it's pretty simple. It's just a spring force defined between two points on two different bodies. And the stiffness can be defined as a coefficient or a nonlinear spline. And similarly, the damping has the two options of being defined by a coefficient or nonlinear spline. And the stiffness and damping exponents can also be set to further define nonlinear behavior. There's also a free length and a preload field, and these can help you model the spring in a pre-compressed or pre-extended position. And so this is just showing the effect of changing the stiffness exponent. It's fairly basic. If you have, on the right here is a plot of the force displacement curve for the springs. And the blue line indicates if you have just a simple linear spring. And then the green and red indicate as you increase the stiffness exponent from 1.3 to 1.5. Now another option is for the stiffness is to use the nonlinear stiffness spline option. And so an example that we can think of here is to use this option to represent coil clash. So as your spring is compressed beyond to a certain point, and the coils start to contact each other. And then what this results in is a much stiffer spring. And so this is can be represented by this curve here. And so if you notice, everything here is in the negative X, negative Y quadrant, because that's in RecurDyn, that's defined as the side that corresponds to compression of the spring. And so this initial curve here represents just the actual spring stiffness. And then at this point where the slope increases dramatically, that's where the coils start to contact each other. And then in RecurDyn, you also have these different extrapolation options. You can choose linear, which is what's being used in this case, or different cubic options, or polynomial options. And so that's what's shown here in this by this orange line here. So when we implement that nonlinear stiffness spline into the spring and compare it to just the regular totally linear spring, these are the results. So the spring on the left is just the standard, using the standard stiffness coefficient, whereas the spring on the right is using the nonlinear stiffness spline. And so you can tell from the behavior that it is modeling that spring clash correctly, because as the sphere sort of reaches a certain point and compresses the spring to a certain length, there's a certain like hard stop that's occurring. So the next standard force entity in RecurDyn is the rotational spring. And that's just simply a rotational spring force defined between two bodies at a point. Again, like the other, like the translational entity, you can define the stiffness and damping using coefficients or splines. And there's also, again, the stiffness and damping exponents. And here we have the free angle and pre-torque fields, which are again used to model a pre-torqued spring. And so basically everything looks fairly similar to the translational spline, except just everything's in the rotational degree of freedom. So an application of this would be, suppose that we want to model this torsional spring shown in purple. And so what's going to happen is that this blue portion of this mechanism is going to fall downwards due to gravity, and it's going to fall freely until it hits that the torsional spring. And then once it hits that torsional spring, then the spring will start to exert a torque upward force on this this body. So to sort of capture that behavior where at some point you have no force applied or torque, and then after a certain point, then you have the torque starting to be applied. We're going to use a nonlinear spline to handle that situation. And so this is what the nonlinear stiffness curve will look like. And so the point on the x-axis of x equals 0 is at this portion. So on this side, you got extension, and then on this side of the plot, that represents compression of the curve. And so for the extension side, it's just simply a flat curve at y equals 0, because the spring will not be exerting any force or torque at all. But then once you reach the point of compression, then that's when the slope has a negative value, representing just a basic linear stiffness for that for the spring. So these are the results of that simulation using the standard rotational spring entity with the nonlinear stiffness spline. And so we can see that the spring entity is simulating the actual spring correctly. So there's no force or no torque, being applied during certain portions until the swing arm reaches that horizontal position, and then that's when the spring starts to apply that torque. So now we kind of move on to increasing the fidelity of the spring modeling. And we can do this using RecurDyn FFlex, which is short for full flex. And so what we can do here is mesh the we can mesh the spring geometry as a flexible body using finite element analysis techniques. And in full flex, all the nodes have their own degrees of freedom, and the mass and inertial effects are fully included in the model. The mesh can be created in RecurDyn using the internal FFlex mesher, which is what I used in this case to mesh this spline. And alternatively, you can also import a mesh from any external meshing software. And contact can also be modeled with the flexible body, between the flexible body and itself, or other flexible bodies, or other rigid bodies. So it's really quite flexible. And just some information about this mesh. This was meshed using a tetrahedral 10 elements. has about almost 7,000 elements and about 14,000 nodes. So here are the results of a simulation using this technique. So what we can see here is that there's a little bit of bouncing of the springs after it returns to its extended position. And so this really shows that we're capturing these mass effects accurately. And another thing that we can also see here is that the contact between the coils is being modeled as well. So you can see at the bottom there, the coils are initially more closely spaced together. So as the spring is compressed, those coils begin to contact each other first, and then more contact occurs at the top later. And so what we can do here is we can compare the results of using the FFlex spring versus a standard spring force. And in order to do that, we first need to come up with a stiffness that we can use for the standard spring force. And so we're going to use basically a test in which we compress this flexible FFlex spring, and then we can measure the required driving force required to compress that spring, which is shown in this plot on the right here. So what we can see from this animation and the plot is that as more coils begin to contact each other, we have a bit of a nonlinear effect that's a result of that, in that the stiffness of the spline or the slope of this curve gets steeper and as we approach the fully compressed position. So the next step would be to take this data and implement it as a nonlinear spline curve in RecurDyn, and that's what's shown here. And so that's then being used as the stiffness for this standard spring force entity. So this is the sort of the base model that we're going to compare the FFlex spring model to. And so here are some of the results at different speeds. So these are the results for 1000 RPM, which is the rotational speed of the crankshaft. And we can see here that the results are pretty similar, which is what we expect because we assigned the same stiffness curve to the standard spring entity. As we increase the speed, here we've increased to 4000 RPM. We can see that the results between the standard spring force and the FFlex spring start to diverge slightly. And the peak contact force at the valve fully open position has also decreased, with this trend being more pronounced in the FFlex spring. And we can also see that the FFlex spring results show a little bit of extra oscillation. And these are due to the oscillation of the spring coils and the resonant frequency that results from that. So now as we progress to an even faster rotational speed, this is 5000 RPM. So now we can see that the contact force after the valve fully open position is now starting to decrease due to the momentum of the valve sort of still traveling downwards. And so that's what's indicated here. And this effect is more pronounced with the FFlex spring case because we're now including the mass of the spring. And so we have both the momentum of the valve and the spring causing this contact force to decrease even more. So now as we move to increase to 6,000 RPM, we can see that this trend is further increasing. And then finally, as we move to 7,000 RPM, we can see that the FFlex curve has a complete loss of contact between the cam and the finger follower. And so this represents the failure condition of the valve floating. And one thing to note here is that with this standard spring force, that failure condition has not occurred yet at this speed. So this is a pretty clear example of using FFlex and including the inertial effects, and by doing so, revealing the failure modes that can't be revealed otherwise. So this is just an animation of those results at 7,000 RPM. And so again, the plot is going to be the cam to the finger follower contact force, which you always want to have as a positive non-zero value. And it's a little bit hard to see. You can see where in the plot where in the cycle the failure occurs, although the separation between the cam and this finger follower is so small that you can't actually see it in the animation. But I think you can sort of tell that that's basically where, sort of at the peak of where things are being compressed, and at where the finger follower is being pushed downward at the fastest value. So now we're going to move on to using FFlex for a torsional spring this time. And this is the same torsion spring that we were looking at before, but now we have it meshed using FEA beam elements. And the reason why we chose to use beam elements is that because this diameter of this spring wire is actually quite small. It's 1 millimeter in diameter. And so when things become that small, in order to avoid the element size being too small, which will result in slow simulations, we can just use this beam element, which will keep the elements at a reasonable size. And another thing that we're able to do using FFlex is to model friction between the wire and the axle. So these are the results of that simulation. And we have the contact force arrows turned on here. So you can see that the contact is being modeled pretty accurately between this the spring wire and the portion, the arms that are swinging, as well as the stationary arm. And what we can also see here is that as the spring is deflected, it starts to constrict around the axle or the pin. And we can see that with these force arrows here. So they really don't kick in until the spring reaches a certain point, and then at that point, as the spring is deflected by enough amount, then that really starts to constrict it around the axle. So again, what we did here was we compared that FFlex spring with the a standard rotational spring force using the stiffness that we can obtain from testing the FFlex spring. And what we can see is that this is a plot of the angle of the swing arm, and the FFlex spring starts to limit the rotation of the arm more quickly, and sort of reverses that direction of the rotation earlier. And also the friction that we modeled between the FFlex spring and the axle also damps out the oscillation more quickly. So we might ask, why does the FFlex spring seem to reverse that rotation more quickly? And that's what we're going to find out here. What we did is to run a test on this rotational spring, and we measured the required torque to deflect the spring. And so what you can see here is as the constrictive contact between the spring and the axle begins to occur, then that really increases the stiffness, the effective stiffness of this spring. And that's pretty evident. There's a particular point right on the plot where you can see that distinct change in the slope. So that would basically result, if we were to take this stiffness information and input it into a stiffness curve, this is what that stiffness spline would look like. So the advantages of using RecurDyn FFlex is that it does include the inclusion of mass and inertia effects, which is critical at high speeds. You can also model contact between the flexible body itself and other bodies, which can then result in nonlinear effects on the spring stiffness. And different element types can be used to suit different size scales. And the meshes can be either created in the integrated FFlex mesher or imported from an external meshing tool. So some of the disadvantages of including all this fidelity in the model, though, is that you're going to have slightly slower run times. So now if we want to sort of include that level of fidelity or close to it, and if we want to have sort of better, faster simulations, we can use the multi-mass Spring Toolkit in RecurDyn. And so this basically this toolkit allows analysts to include this high fidelity spring modeling, including the mass and inertia of the spring coils, as well as contact between the coils. And there are multiple model types available for the Spring Toolkit. There are about 4 different types, but in this case, we're going to cover what's called the type D. So for faster simulations, what this toolkit does is it automates the construction of these segmented spring bodies, which are rigid bodies. And then the rigid bodies are connected with beam forces to represent the stiffness of the spring. The beam forces are Timoshenko based, and they are characterized by the material properties such as Young's modulus and shear modulus, as well as the geometry such as the cross-sectional area. And so this example here that we're showing is of a dual valve spring. So they're actually, there's an inner spring and an outer spring. And again, we can see the effects of the mass of the springs as they bounce around after the valve is closed again. So as far as the options for modeling these springs, this is what the controls look like. You're able to model the basic overall shape of the spring or the center line of the spring coils by 2 different methods. And the first is you can enter various parameters such as the pitch angle, and you can also, actually in this particular case, you can have kind of a dual rate spring with 2 separate sections of coils with different pitches. And then the second option for more complex designs is to actually enter in a skeleton profile information. So you've got sort of the angle, height, and the radius information entered. Another option that we have here with the toolkit is to model a suboval cross-section of the wire. So that's what we're seeing here. Here, the thickness of the wire is 2.5, but the width is actually 3.4 millimeters, so it's a little wider than it is tall. And then here are some of the controls for the parameters between the parameters controlling the contact between the coils. So stiffness, damping, and friction can be defined. And then here's where we would enter in the material properties that characterize the Timoshenko-based beam forces. So once again, we're going to take the same approach of comparing this MMS type D spring to a standard spring force that has the same stiffness. And so this is, again, at what we're looking at is the contact between the cam and the tappet. And this is at 1000 RPM. And we can see that this is at a slow enough speed where the results are quite similar. As we increase to 9000 RPM, we can see some similar trends to what we saw before. The force profile sort of reverses itself in that you've got, instead of being high in the middle, now is low in the middle, and there are some initial and final spikes surrounding the valve lift event. And the reason for this is due to the inertia of the valve and the tappet. And then in the case of the MMS type D spring, the inertia of the coils of the spring add to this effect. So that's why this red line here is even lower than the blue line. As we increase slightly from 9,000 RPM to 9,750 RPM, the MMS multi-mass spring type D spring shows a complete loss of contact, which again indicates a valve float failure condition. And so that's shown in the plot here, where the contact force goes all the way down to 0. And once again, the standard spring force does not capture this behavior. And so this is an animation of those results. Actually, this is for 10,000 RPM, just to kind of show the effect a little bit more obviously. So here you can definitely see there's a separation between the cam and the tappet here. And you might wonder why in this case are we seeing, compared to the FFlex spring results, we're able to see this valve float more pronounced. And so one reason why that could be is that the FFlex spring was actually a beehive spring, which had smaller diameter spring coils at the top of the spring. And this design is intended to reduce the mass effects of the spring. So what we are seeing here is that RecurDyn is capturing these effects of the different designs of the springs correctly. So some advantages of using the multi-mass spring toolkit is that you do have that higher fidelity modeling where you're including the mass and inertial effects, as well as the contact between the spring coils. And also another advantage is that you can quickly change the spring geometry by changing the parameters that we saw earlier. And because this approach has less degrees of freedom included in the model than the FFlex approach, it's going to result in pretty fast simulations. So in conclusion, I think what we've seen here today is that the springs can be modeled in RecurDyn with varying levels of fidelity and simulation performance. The standard spring force entities offer excellent simulation performance. Most of those simulations were actually completed in less than a second. And the MMS spring toolkit is sort of the middle ground where it can be used to quickly simulate springs with a higher level of fidelity. And both the approaches above can be used in larger system models where there are many springs. And then if we really want to include all the fidelity in the model, then we can use RecurDyn full flex or FFlex. And FFlex has the ability to model the largest variety of springs with different geometries. So it can be used to model the torsional springs or the coil springs, or even such things as leaf springs. So I hope that gives you a good idea of the capabilities of modeling springs in RecurDyn. And so at this point, thanks for your time. And if you have any questions, feel free to ask them.
Awesome. Thank you, Nelson. We do have a few questions to get to. First one being for the FFlex valve spring, how was it constrained in the model?
Sure. So that was constrained with contact between the spring and the bodies above and below it. And then there was also used what's equivalent to a Nastran RBE3 element, which is sort of an interpolation element that was used to keep the spring from drifting off center. So those, so the master node for that RBE3 element was constrained with an inline constraint, sort of vertical, to restrict the motion to vertical motion only. And then the slave nodes were then sort of the bottom surface of the spring.
Okay, and the next question that came in, what can I do if I want to include the fidelity of FEA-based springs, but the runtime is too long?
Right, that's a good question. So what you would want to do is to, you could have your FFlex model, and then you could run it through a series of tests where you're taking it through the full compression and extension, and then measuring the required force to compress the spring. And then you can also run it through that same motion at varying speeds. And then you can, from there, you can derive the damping spline. And then you can use that information and input it into the basic spring entities in RecurDyn, which will give you the best simulation performance.
Okay, great. And here's another question. How did you achieve smooth contact on the CAM or tappet interface?
Yeah, the contact was a 2D contact. And that was just for the highest simulation performance. So the 2D contact, meaning that you're representing the curvature of the cam with just a single profile curve, and then the top of the tappet just had like a straight line that was. And so we're modeling contact between those two 2D elements.
Okay, and then I think we have a couple more questions. How long did the simulations take to run, Nelson?
Yeah, sure. So the standard spring forces were very fast. They're like less than a second. The MMS type D simulations took around 4 to 6 seconds, depending on the speed of the RPM of the engine. And then the FFlex valve spring took between 18 and 50 minutes, again, based on the speed of the rotational speed. And for the FFlex torsion spring, that took about 6.5 minutes.
All right, awesome. And the last question we have here, for the Spring Toolkit, do we need any information beyond a typical Spring data sheet?
I wouldn't think so. I think you could probably get most of what you need from just the existing Spring data.
Okay, very good. Well, that's all the questions that have come through. And anything else to add, Nelson?
No, I think that's it. Yeah.
All right. Well, everybody, I thank you again for attending our Springs webinar. I hope you guys have a great rest of the day. And as always, if you have any questions, you can reach out to us. Our website is enginesoftusa.com. Feel free to get our contact info there. And other than that, I hope you have a great rest of your day. Thank you, everybody.